Hello, let's learn about lasers. Now there's a variety of different types of lasers, but we're going to look at the two main types, and there's a lot of similarities between those two as well. So this is an example of a simplified version of a laser. What you basically have is a gas discharge tube in that there's a chamber that's been evacuated, and then a small amount of gas has been reintroduced to it at low pressure, so helium neon mixture, and you have two cathodes, or cathode and anode, two electrodes with a voltage, high voltage across them, plus a small amount of current. So electrons are whizzing between these, colliding with the gas atoms and causing them to be excited, and then you get the whole excited process happening. You also have, and so photons are being produced, and what you have is two mirrors. One mirror is 100% reflective, so any photons that hit this mirror bounce back and go through the tube again, whereas this one is only about 95% reflective. So only 5% of the photons go through and the rest are bounced back. And this whole bouncing backwards and forwards is important because that's how you generate the laser beam. Another type is similar, but in this case you have to have what's called a flash tube, and effectively it's like a flash on a camera. It produces a large amount of photons very quickly, and that flash tube flashes onto a ruby crystal, and you have the crystal is polished, and then each end of the ruby crystal is mirrored. One end is 100% and one is 95%, and you have the power supply for the flash, and this basically is constantly flashing and producing photons, exciting the ruby crystals or the atoms within the ruby crystals and producing a laser beam. So similar but different. These are the earliest type, and you'll find them in lots and lots of things. They can be miniaturized quite successfully into very small, as nowadays most lasers can be. So how does a laser work? Well, first of all, what does laser stand for? The word laser didn't exist until someone invented a laser, and they named it by calling it after the process, which is light amplification by stimulated emission of radiation, and they shortened it to laser. And lasers generate what's called a coherent beam of light. Now by coherent it means that all the photons are all in sync in terms of their vibration, their plane of vibration, and where they are vibrating or how they're vibrating. So they're all synchronized, and that means that the beam has different properties. Like if you just have a beam coming out of a torch, for example, or a light globe, you're getting lots of photons, but all those photons have different orientations, are all in different phases of their wave cycle. Whereas a laser, all the photons are exactly the same in exactly the same phase part of their cycle. So they're in phase with each other. Yeah, there you go. Within a laser, the atoms are excited to a higher state, so that there's what's called a population inversion. So for the laser effect to occur, you must have more atoms excited than there are unexcited, and that's where the population inversion occurs. And we're going to look at a diagram shortly, or right now in fact, of what we mean by that. And so in a normal electron population, you have most electrons are down in the ground state, but because there's energy around all atoms, some electrons will be up in the higher energy state and they'll drop back down, and some will replace them, and so forth. In an electron population inversion, more electrons are in the higher state than in the lower state, and you have more atoms excited in this state than you have in this state. And so that's the population inversion, because you must have each of these dropping down electrons produces the photon which you need to have stimulated to get the emission of radiation. Now the excited atoms are stimulated to release their energy by a photon of the same energy, and this is what happens inside the laser. It's called stimulated emission. So if we go back, if if we go back, so all these electrons will sit up here and they'll just casually drop back depending on how much energy is in the whole system. But if a photon comes past that has exactly that drop in energy, it will cause this electron to drop and emit a photon. And so from one photon of that energy going past, you then generate another one and you end up with two, and the stimulated photon is in phase with the photon that caused the stimulating, if that makes sense. So this is what we're trying to show here. This photon has exactly this is the first stage. This is the absorption. So the electron absorbs this amount of energy from the photon, jumps up to the higher energy state, and normally it would just jump back down with time and emit the photon of corresponding energy. Now with lasers, what happens is that you've still got this excited electron up here, but a photon goes past, stimulates this to fall down, and you produces a photon, but you've still got the second photon because its energy hasn't been absorbed. So you now got two photons that are in phase. Now if this is happening with gazillions of atoms, excited atoms within the laser, you're getting a massive amount of photons all in phase. And yeah, we've said that. So these photons then bounce off the end mirrors, causing more simulated emission, and you produce a coherent monochromatic. Monochromatic just means it's only of one wavelength, and depending on how good the optics are, the beam is parallel and won't diverge very much once it's been emitted. And so this is another diagram showing it. So you what have we got? Got a large potential difference. You're exciting some of the atoms. A photon comes along, causes an excited atom. Here's an excited atom. Photon comes along, produces two photons. Those photons then excite other atoms, and so you have an exponential growth. And these bounce off the mirrors, go backwards and forwards, and some of them are transmitted. Simple enough. So on the OneNote there should be some videos. One's about popping balloons and popping balloons inside balloons, and then there's one about the airborne laser that was proposed as part of a missile defense system, and it was quite topical, and the Americans spent billions of dollars trying to develop it, and it produced probably the most powerful laser ever. And it had to be really small so it could fit in a plane, a great big plane, so it was actually very big, but now it's been axed because it was basically too hard to do and too expensive for the success rate that it promised. But there's a video about it, which I think was made a little bit before it got cancelled. And lastly, there's there should be another one of bouncing it off the moon. Sending a laser through a telescope, bouncing it off a reflector put up there by the Apollo missions, and getting it back and measuring the Earth-Moon distance, which is quite an important thing, used in a lot of situations, particularly dealing with satellites and GPS and things. So those videos will be on your OneNote, and in the next video we're going to look at fluorescence and phosphorescence. See ya.